Okay, team. So in the previous session, we had started divide and conquer, right? Majorly parallel divide and conquer, because we said it's better if we look at divide and conquer from the parallel algorithms perspective, because if a problem is broken down into multiple subproblems, often what happens is these subproblems are independent of each other. If they are independent of each other, that means there is no dependency, then you can execute these function calls in parallel, right? And so we looked at a couple of parallel divide and conquer problems and solutions. And in most of the cases, what was the core idea? Split a problem into multiple, two or more subproblems, and often these are independent subproblems, but a divide and conquer does not mean they have to be independent, right? They can be dependent on each other, but typically they will be independent, and then we can execute them in parallel, and we get the solutions to these subproblems. We combine these solutions to subproblems to construct the original solution to the original problem, and that is our divide and conquer. And we looked at array sum and in general parallel for loop, right? And we had started looking at recurrences. And in this session, we will look at recurrences. We will complete merge sort and quick sort, divide and conquer algorithms. Okay. And the complexity analysis, what we did was we defined 4 types of complexities. Cache complexity, we will not worry. So one is work complexity. Work complexity is the runtime on a single processor. It is same as our normal running time. However, we have been evaluating these running times. The second is the depth. Depth is the parallel running time or running time on infinite number of processors. And it was just one simple extension, right? If there are multiple function calls doing or solving the problem on a similar problem size, we consider that as one call, right? And that's how we define depth and found complexities for depth. And then we have space complexity. Space complexity, often it will be similar to work complexities, right? All right, often. Okay, now we said we are going to define one single theorem that will be used to solve thousands and thousands of recurrences in one shot, and that is the master theorem. So the master theorem you can apply whenever the recurrence is of this form. T of n is equal to a t of n by b plus f of n, right? Where n is greater than or equal to d for some constant d. What are these values? A is a real constant greater than or equal to 1. B should be at least greater than 1. You can see 1 plus epsilon, where epsilon is greater than 0. And f of n is a positive function, right? What else? So note these. Though the recurrence is defined for a and b arbitrary real numbers, but in our divide and conquer algorithms, we see that these, say b, the problem size is decreasing by a constant factor, right? B can be 2, B can be 3, 4, so on. And A is 2, 3, 4, so on, right? It can be any real constant. It has to be a constant. What if it is a function? Suppose A is not a constant or B is not a constant. What if it is a function? Right? Then you cannot apply this master theorem directly. It might get more complicated, right? If it is a function, we cannot directly apply. What if B is 1? B is 1, we saw that it goes into an infinite recursion, so we cannot solve that recurrence directly, right? Okay, what if A is negative? What if a is negative? Or if a is less than 1? Its master theorem is not defined for such values, right? A is negative. What is the meaning of A is negative? So here, T of n, typically it means the running time. And running time is positive, right? Running time is positive because the number of computations is positive. Hence, we have taken only one class of these recurrences that are important to analyze the runtimes or space. Space is also positive, right? When n increases or some input parameter increases, the space increases or time increases. Communication complexity increases, so on. So we assume all these are positive functions, right? If it is negative, what if it is negative, right? What if it is not plus? What if it is negative? If it is negative, it depends. If it can go negative, right, minus f of n, this overall expression, then it's no longer a positive function. Leave master theorem, we cannot even apply our asymptotics. Why? Because for asymptotics, we assumed positive functions, right? So you should be careful. So just because you're given a recurrence that has similar to, a t of n by b and some operator f of n, it doesn't mean you can always apply master theorem. First, you need to check if it is of the form where you can apply master theorem, and only then apply it based on this. So here we will call this as case 1, right? This is case 1. This is case 2. This is case 3. We said there are 3 cases. Assuming all these constraints are satisfied, we have 3 cases. What are these 3 cases? So we defined delta as log A base B. Look at this, A is a constant, B is a constant, delta should be a constant. Okay, if delta is a constant, n power delta, what is n power delta? The n power constant is a polynomial. Polynomial. Okay, what about f? F of n, should it be a polynomial? It may or may not be. In many of the cases, we see that they are polynomials, n, n squared, so on, but it need not be a polynomial. It can be, say, log n. Log n is not really a polynomial function, but it is upper bounded by a polynomial function. What about e power x? E power x is not a polynomial function. So it can be really any positive function, right? But n power delta, so if we consider n power delta, that's a polynomial. So what we are doing is we are comparing n power delta and this function f of n. We are really comparing n power delta and f of n. Then we have 3 cases. So let me show this slide. F of n is polynomially smaller than n power delta. You know what is smaller, right? It's asymptotically smaller. So what do you mean by polynomially smaller? What is the difference between asymptotically smaller and polynomially smaller? Polynomially smaller is one type of asymptotically smaller. Okay, what type? It is asymptotically smaller by a polynomial function, right? So it's f of n is definitely asymptotically smaller than n power delta, but not by something like log. It has to be smaller by a polynomial function, maybe say n power epsilon, for some epsilon greater than 0, right? So f of n is polynomially smaller than n power delta. So another case is f of n is polynomially larger than n power delta. So these are kind of opposites, right? Opposites. If f of n is polynomially smaller than n power delta, n power delta is the winner because it's larger, right? Asymptotically larger. Okay, if f of n is polynomially larger than n power delta, f of n is larger. That is the winner. What if f of n is asymptotically close to n power delta? Then it is f of n times log n. But where did we get log n from? Why don't we just have f of n? Right? The reason we have log n is because in our final derivation of the complexity T of n, we have a sigma factor, a sigma term. That sigma, look at this. That sigma is something like this. It has log factor. When you simplify, right, substituting all these values and simplify, that log factor comes from this sigma, the summation, multiple terms, right? So you get extra log n factor because of this sigma. Okay, but that sigma is there in case 1 and case 3 also, right? True. But because of the condition that will not dominate, remember in a geometric series, you can have a summation, but okay, let's consider this geometric series 1 plus r squared, so on up till plus r power n. What is the complexity of this? The complexity of this is theta of, okay, before writing theta, what is the exact formula? Maybe something like this. You need to verify it. R power n plus 1 minus 1 by r minus 1. Right? R power n plus 1 minus 1 divided by r minus 1. So in terms of theta notation, you can see it is r power n. It's kind of dominated by the largest term. Maybe it is 2 power, r power rn and all. So when r is equal to 2, you will see that it's kind of approximately equal to 2 times 2 power n, that is 2 power n plus 1. Right? So try out for different values of r here. So it's dominated by the largest term. Right? So similarly in case 1 and case 3, that sigma notation, right, will not dominate, that log number of terms. Here also there are so many terms, they do not dominate, right? Only the last term dominates. So case 1 and case 3, you don't have any log factor, right? Because it's something like this, geometric series, right? Whereas it is something similar to geometric series, not exactly, but look at this. This is the series, okay? But in case 2, if f of n is asymptotically close to n power delta, we see that all these terms are approximately have the same value. So hence this log n term will come into the equation, right? So that's the higher level intuition. So we will not go into the rock bottom details of the derivation and all. That is unimportant. What you want to practice here a lot is how to apply it on problems, because in the future you will be seeing a lot of divide and conquer problems. And divide and conquer problems or algorithms are analyzed using recurrences. How do you solve these recurrences? We looked at a couple of methods, iteration and substitution, recursion tree, but all those are complicated, right? For each and every divide and conquer program, you cannot do all these things. It will take several pages, right? It's a waste of time. So you want to quickly apply this theorem and get the complexity in one shot, right? That can be the work complexity, it can be the space complexity, and so on, right? So that's the idea. Okay, let's come back to this recursion tree. We we saw the recursion tree for a particular example, right? Remember, we saw this recursion tree for a specific recurrence. Generalizing it, if we generalize it for this very generic form of recurrence where we can apply master theorem. So you have this recursion tree where it's a decision tree, right? A recursion tree looks like a decision tree. It's a recursion tree where the branch factor is a. What is the meaning of branch factor? Number of child functions. Number of neighboring functions is a. And in every level, the problem size is decreasing by a factor of b. It keeps decreasing until the subproblem size is constant, right? It can be 1, it can be 2, it can whatever. So here we have written 1 for simplicity, right? Okay, now we have this recursion tree. We look at the total amount of work done in all the leaves. Where is the work done? The work done are in the leaves. Each leaf does some work, right? Does some computation. And also the work is done in dividing and conquering steps, right? The work is done because it takes a split, or maybe you're partitioning, or maybe you're combining the solutions, merging. All those operations will require certain amount of computations. So the work is done in the base case leaves. So each leaf node represents a base case. So the total number of base cases times the work done in each base case. The work done in each base case, say it is constant. Let's assume it is constant. So the total number of leaves will be what? N power log A base B. And why is it? So if you simplify, the branch factor is A. The branch factor is A. The height of the tree is log n base b. The height of the tree is log n base b. When you simplify, you get n power. Okay, let me write it as branch factor power height gives you the total number of base cases here. Branch factor power height. Branch factor is a, height is log n base b, right? If you simplify, you get n power log a base b is equal to n power delta. Total number of base cases is this. Or you can say the total amount of work done, computations in all base cases is this. Okay, what about the total amount of computations in dividing a subproblem and combining subproblems? At level 1 or say level 0, it is f of n. Because you're getting all these child functions, that means you need to do divide. You need to divide the problem into subproblems, and you are combining all those solutions, right? Combining all the solutions. For these, it will take f of n time. So that's the meaning of it, right? T of n is equal to a times T of n by b plus f of n. And similarly, in the next level, there are a number of leaf nodes, Each leaf node is has subproblem size n by b. So the total computation is f of n by b for one subproblem. There are a number of subproblems, so a times f of n by b. Okay, at the next level, there are a squared number of subproblems because the branch factor is a. And so each subproblem does f of n by b squared amount of work for dividing and combining because the problem size is n by b squared. So total amount of work done at this level is a squared f of n by b squared. If you keep doing it, right? So you get a power log n base b minus 1. The height, right? What is the height? Log n base b. So height minus 1, a power height minus 1, f of n by b power height minus 1. And add this sigma notation because you need to sum all these computations. You're doing it at every level. There are approximately log n levels. So add all these computations. So the work done in the base cases plus work done for dividing and combining the subproblems is the total work done by any divide and conquer algorithm, right? Okay, so in some cases, depending on the recurrence, this can dominate the base cases, or in some problems, this can dominate, right? So that's why we have 3 cases. So check whether n power delta dominates, or check whether f of n dominates, or if all these are equal, then there are log n terms. So it will be n log n times f of n, right? 3 cases. We have 3 cases. Okay, so let's take a look at some of these examples. First, tell me whether you can apply master theorem or not. And then if you can apply, how you can apply, right? Okay, what about first problem? So what do you think, team? A is equal to 4. A should be greater than or equal to 1, right? That is true. B is equal to 2. B should be greater than 1. It is true. F of n, what is f of n? It is n. So yes, everything is satisfied. All these 3 constraints. You just need to look at 3 constraints. A, B, f of n. Majorly. I mean, there can be other things, but depending on the problem, but majorly these 3 things. Yes, all these are satisfy the requirements for master theorem, so you can apply master theorem. Okay, now let's compute delta. What is delta? Log A base B. So what is this? Log 4 base 2 is 2. Is this correct? Now you compare f of n and n power delta. You see that f of n is O of, or say theta of n power delta minus epsilon, where epsilon is equal to 1. Is this correct? Is this correct, team?
Yes, it is correct.
Right? Okay, so can we say that f of n is upper bounded by, or O of n power delta minus epsilon for epsilon greater than 0 from case 1? Case 1 of the master theorem will apply, right? Because theta,
Yes.
we can replace it with O, of course. So if we have theta, we can replace it with O, but if we have O notation, we cannot replace it with theta, right? Please make sure all these cases work. Okay, next. So this is case 1 of master theorem. So what is the complexity? The complexity is what? Theta of n power delta. What is n power delta?
N square.
n squared. Is this correct? Right? Verify it. Okay, now let's consider so last case. What about this case? T of n is equal to 2t of root n plus log n. How do you solve this problem? How do you solve this problem? What is A, what is B, what is f of n?
A is 2, B is half, Fn is log n.
So A is 2, B is half, f of n is log n. Is this correct? Is B 1 by 2?
No.
Right?
No.
It should be of the form n by b here, right?
Yeah, that's right.
So it's root n. If it is root n, so it's not b is equal to 1 by 2, it's root n. So it cannot be written in the form n by b directly, right? Hence, we cannot apply master theorem directly to this recurrence. Make sense? So you need to make sure that the recurrence you are given adheres to the template, right, or form of the master theorem. Okay, what about, okay, let's consider this. T of n is equal to T of n by 3 plus n. A is equal to 1, B is equal to 3, f of n is equal to n, right? What is delta? Log A base
0.
B is log 1 base 3 is 0. So n power delta is n power 0 is equal to 1. So you want to compare f of n and n power delta. You see that f of n is at least n power delta plus epsilon for epsilon is equal to 1. Is this correct?
Yes.
Right? Because f of n is n power 1, omega of n power 1 plus
0.
Sorry, the 0 plus 1, right? So which case is this?
Is 3.
So this is the third case, right? This is the third case. Satisfies case 3 of master theorem. It satisfies case 3 of master theorem. So if it satisfies case 3 of master theorem, what will be the final complexity? N? Is it n? It's theta of f of n, right? It's theta of f of n in case 3. F of n dominates. If f of n dominates, then it's theta of f of n in case 3, right? Okay, so try to solve this problem too. A is equal to 2, B is equal to 2. So this is greater than or equal to 1, works. Greater than 1, good. F of n is n log n. Okay, now what is log A? So delta is equal to log A base B is log 2 base 2 is 1. So we are comparing f of n and n power delta. So n log n. Okay, let me write it like this. N log n and n power delta, that is n power 1, that is n. We are comparing n log n and n. They are asymptotically, very near, right? Just in the log factor, not polynomially larger or polynomially smaller. You see that, right? It's neither polynomially greater, it's neither polynomially smaller. But of course, f of n is polynomially larger. Okay, now think about what will you do. So what will you do here? So take this as homework, right? So we will, in the divide and conquer, next homework, we will give a lot of recurrences. So try to analyze how to solve these kinds of problems. So we will show a couple more examples later. Okay. So continue from this, take this as homework, but we will give more such problems in divide and conquer. Okay. So next, I will skip stud sort as of now. If we have time, we'll come back. Let's start with merge sort. Merge sort is a very famous divide and conquer algorithm. It's a very good algorithm. The worst case time complexity, here we call it the work complexity, right? The worst case time complexity or work complexity of merge sort is n log n. N log n number of comparisons only. So if you remember, we covered insertion sort and we covered bubble sort, we covered selection sort. All these three algorithms have the worst case complexity of n squared number of computations. And another algorithm we saw was heap sort. Heap sort had the worst case complexity of n log n. So heap sort was the first sorting algorithm we saw that had a complexity that was better than n squared, asymptotically better than n squared. And we said heap sort is a great algorithm, right? N log n number of computations only, not more than n log n. So here we will see another algorithm, the second algorithm that has n log n as the worst case complexity for sorting. So this will be the fifth algorithm we will be covering, right? So if you have studied algorithms and data structures, you should have completed at least 7 or 8 sorting algorithms. We will cover quick sort also, that will make it 6. And later, you can also study, some more algorithms. Stud sort, if possible, we will cover stud sort, that will be 7th. And I did not cover counting sort, that will be 8, right? So try to increase your knowledge on sorting algorithms. There are probably over 100 sorting algorithms. But if you're in computer science and if you're learning about, not in computer science, if you're learning about algorithms and data structures, you should know around, say, 8 sorting algorithms, because different ideas, right? It's about problem solving, it's about understanding, thinking, and so on. And here is our very favorite merge sort. And so I don't know if I covered this or not. Probably I did in trees, right? External memory algorithms. I said one of the famous interview problems is, how would you sort a 10 terabyte file of numbers that is on your hard disk, right? That's a famous interview problem. Google, Microsoft, and all frequently ask these kinds of questions. How would you sort a file of numbers that is not in your RAM? See, if it is in your RAM, you can just allocate space, sort it by any of these algorithms, and right, you can solve the problem. However, if the data is in hard disk, how would you solve the problem? every time you want to bring pieces of data into RAM, but suppose your RAM stores only 512 MB, but you have a 10 terabyte file of numbers. How would you sort? The most famous external memory sorting algorithm is external merge sort. See, so merge sort is not only good at the RAM level, it is also great at the disk level, right? So the algorithms that we study are internal memory algorithms. That means we assume that the data is in RAM. You know about RAM, right? At least the basics of RAM. So merge sort, a kind of variant, it's called external memory merge sort, that is also used when the data is in hard disk. Okay, remember that. It's a very important point, very useful point also. Okay, so that is the power of merge sort. Still, merge sort is not extensively used in programming languages. Whenever you call the sort function, sort API in your programming languages, it's typically not the merge sort that will be called. It will be the quick sort that will be called, or some tiny variant of quick sort. Why? I mean, even heap sorts are not used in programming languages most often. It's the quick sort. Why? Heap sort is n log n, merge sort is n log n, but the worst case complexity of quick sort is n squared. But still, programming languages use quick sort and not really heap sort or merge sort. Why? Okay, so we will analyze all these things later once we cover quick sort also. But now, right, let's cover merge sort. So this is the subproblem. This will be the subproblem for most sorting algorithms. You're given a subarray and you want to sort it. And your aim is to sort the entire array, A of 1 to n, the first indexing to the last indexing, say n. So here is the core idea. You have the entire array. Suppose there are 8 elements in our array. You want to sort them. What do? You split. You split the array into 2 equal halves. The first half, and the second half. And split is dead simple, right? Just add a brick. That means you call the first half of the array here, second half of the array here. In programming language, it's nothing. You're just giving the indexing of these array. You're just giving the indices, right? Nothing else, because you always send arrays by references. So you don't need to worry. It's not copying the array. You're just giving the index numbers. Okay, first half and second half splitting is dead easy. It's constant time operation. And then you recursively sort the first half, recursively sort the second half. And this is the conquer step. Conquer step is always a recursive call. Okay, so magically it sorts the problem. I mean, recursively means it again recursively subdivides, right? Subdivides this and so on. Suppose it sorts the subproblem and it sorts the second subproblem also. Now you have a sorted subarray and another sorted subarray. You have 2 sorted lists or 2 sorted arrays that you merge. This is the combined step. Combined step is complicated. Divide is dead simple. Conquer is just recursive calls. There is nothing there. Parallel recursive calls. And conquer step is the most complicated operation in the merge sort, that you're merging here. So what is this conquer step? You are given 2 sorted arrays You are given two sorted lists.
Professor, you mean combine, right?
Yeah, combine a stage of divide and conquer.
Okay.
Right? See, we defined divide and conquer in three stages, right? First step was divide, second step was conquer, third step was combining the solutions of the subproblems. So that is the meaning we are talking here. Right? That combining step is really the merge in this merge sort. We are merging. What do you mean by merge? We are given two sorted arrays. We want to construct a sorted array from these elements. See, 2, 4, 5, 7, 1, 2, 3, 6. When we merge them, we get a sorted array. 1, 2, 2, 3, 4, 5, 6, 7. Right? Now, this is the most complicated step. That is the combine step of this divide and conquer. That is the merge step here. Okay. Now, let me go to the code directly, the pseudocode. The pseudocode is something like this. Suppose the array indexing is from 0 to n minus 1. Right? 0 to n minus 1. 0 to n minus 1 is any array, unsorted array, and you want to sort this array in non-decreasing order. What do you mean by non-decreasing order? What is the difference between non-decreasing and increasing? Increasing is something like this: A1, A2, A3, so on. Non-decreasing is something like this: A1 less than or equal to A2, less than or equal to A3, so on. Right? So non-decreasing means something like this, because there can be duplicates. It's not that the array is full of unique elements. It can have duplicates. If there are duplicates, we have to order them like this, right? In non-decreasing order. Okay, so what is the idea? If there is only one element in the array, you don't need to sort. If there are two or more elements, only then you need to sort. So if n greater than 1, then take the first half of the array a of 0 to n by 2 minus 1. I mean, you can work out the indices later, right? So use some examples. What if n is even? What if n is odd? See, n need not be a power of 2 here. N can be arbitrary natural number. Need not be a power of 2. Right? But we explain it for power of 2, taking examples of powers of 2, because it is simple to visualize and analyze. Right? Okay. So take the first half of the array, copy it to B array. Take the second half of the array A and copy it to C array. And B and C have approximately equal number of elements. Why did I say approximately equal? Because if n is even, then they have equal number of elements. If n is odd, they cannot have equal number of elements, and the difference in the number of elements and B and C is 1, if n is odd, right? But you can say B and C have approximately equal number of elements. So this is one subarray, this is another subarray. So this is the divide step, step 1 or stage 1, divide step of divide and conquer. In the conquer step, what is a conquer step? Conquer. So this B array and C array are completely different arrays. So we recursively sort them, sort of B and sort of C. And look at this, the number of elements in B and C are approximately half. the number of elements in A, right? And because B and C are independent arrays, we can run these functions in parallel. Parallel call to sort of B and parallel call to sort of C. Okay, that's the conquest step. Conquest step is nothing but recursive calls. Done. Dead simple. Third, we want to combine. Okay, so after this conquest step, we assume that B array is already sorted. After this call sort of C, we assume that C is sorted. Now what do? Merge ABC. That means we take the B array, we take the C array and merge them into the A array. Take the sorted B array, sorted C array, and merge them as shown in the diagram, right? We get the sorted A array. So at the end of this call, the A array, original A array, will be sorted. So we just need to understand this merge function and we are done with merge sort, right? Divide is dead simple, constant time. Conquer is, you can assume if this is T of n, you can assume this is T of n by 2, T of n by 2. And conquer step is slightly complicated here. Maybe it is complicated, maybe it is simple, we will see. If we understand combine, we are done for the merge step here, right? Okay. Next. Now let's come back to diagram. So we know the core idea here. We have seen how to convert this into the pseudocode. We just need to understand the merge step and we are done. Now let's look at the execution of the algorithm on a particular example. So here is our big array 5, 2, 4, 7, 1, 3, 2, 6. Split them into 2 equal parts and recursively call them. That recursive call to this, see, this is a recursive call. This is a recursive call. In this recursive call, what happens? Again, you split it into 2 equal halves, 5, 2, 4, 7. Again, split it into 2 equal halves, 5, 2, 4, 7. Right? 5 will be sorted. If it is one element, it's automatically sorted. Right? Element with 2 automatically sorted. Now you have an array that has one element. You have another array that has one element. Right? You merge them. You get a sorted subarray, 2, 5. And this after merging will be 4, 7. Right? So this is one function call. This is one function call. And we are done with this. Now this function call gives you 2, 5 as the result. See, 5, 2 is sorted as 2, 5. So in this function call, 4, 7 is sorted as 4, 7. Now here is one subarray, 2, 5, and here is another subarray, 4, 7. We merge them to get 2, 4, 5, 7. So we do the same steps in the second call here, and we get the sorted sublist or subarray as 1, 2, 3, 6. So we have this sorted subarray 1, sorted subarray 2. We merge them to get the sorted array for the original problem. Right? So here is the example. So what we don't understand is how the merging is done. How is the merging done? Let's define the problem again. We are given 2 sorted arrays. We want to combine them and merge them into a single sorted array. Okay, suppose we are given a sorted array B. Suppose we are given a sorted array C, and how do we get from these? How do we combine the elements of these to get another sorted array A? Right? So that's the idea. So, I mean, that is the problem. So suppose the B array has P number of elements. Suppose the C array has Q number of elements. And what we do initially is we will have a pointer. See, this is the pointer. I for B, J for C, and K for A. We will have different pointers. I and J are used for scanning and comparison. K is for filling. We want to fill this array A, right? So what do? Take the first element of B, take the first element of C. Compare whichever is smaller. Here we are comparing B of I and C of J. One is smaller. One is smaller. So what you do is copy this element 1 to A. That means in A of K, you copy this element. You already added 1, right? So move the pointer. Now J points to 2. We are done with this element. So J points to 2. I is still pointing to 2 here. Now compare B of I and C of J. Look at which is the smaller element. Okay, 2 is the smaller element. You can arbitrarily choose, right? Any of these because they have the same value. Let's assume we incremented, okay, so let's assume we are taking the element of B. So that was 2. We place that 2 in A array and increment the pointer I. Because we added this element, we are done with this element. Let's move the pointer. I points to 2 here. J still points to 2. So, is this correct? Right? Now, again, compare B of I and C of J. What do we see here? We see a 2. Again, arbitrarily choose one of these elements. I mean, here in the logic, we will always get the elements of B. If they have the same elements, we will get the elements of B then. So increment the pointer, add that 2, right, as the third element of A, increment the pointer. Now I points to 5 and J points to 2. What is the smaller element? 2 is the smaller element. Copy this element here, right? That is the next element of A, and increment the pointer J. That's it. So you just have 2 pointers, one for I for B and J for C. Now compare B of I and C of J. If B of I is less than or equal to C of J, copy the B element to A, right? A of K here, and increment the I pointer. If you are getting the element from C of J, that means if C of J is less than B of I, copy the element of C of J to A of K and increment the J pointer. That's it. So I is a scan, right? I scans the entire B array from left to right. J is a pointer that scans C array from left to right. Okay. At every step, we compare the elements pointed to by I and J. Whichever is smaller, we copy it to A and move the corresponding pointer. If I points to the smaller element, copy it, move I. If J points to the smaller element, copy it, move J. Keep doing this. Keep doing this. At the end, what happens? Okay, suppose I is equal to, say, I points to 5 and J points to 6. Now what do we do? Okay, suppose we compare B of I and C of J. We saw that 5 is the smaller element, so we copy 5 to the array A and we move the pointer. We see that I has scanned all the elements in the B array. There are no more elements to scan. Then what is the meaning of that? That means all the remaining elements of C can directly be copied here. Right? If I reaches the end before J does, copy all the elements of the remaining elements of C to A. If J reaches the end of C before I does, then copy all the elements of B to A. So does this make sense? So it's just a linear scan of B array, a linear scan of C array, and a linear scan of A array. So if B array is of size P, C array is of size Q, A array should be of size P plus Q because it's the combination of all elements, right? Merging of all elements. What is the time complexity of this merge function or algorithm? It's theta of P plus Q. Theta of P plus Q. Though we have defined this merge function for two arbitrary input arrays, that means two input arrays of arbitrary size, right? I mean, they should be sorted and they can have arbitrary size P and Q, then it's a linear algorithm, right? Linear scan, linear time algorithm. But here in merge sort, we know that the difference between P and Q is at most 1. P is equal to Q, or P is maybe Q plus 1, or P is Q minus 1. So, I mean, some of these cases are true, right? Depending on how you code it, right? That's it. So these P and Q are not arbitrary kind of independent variables, but in our merge sort. But still, we defined a very generic merge algorithm that works for arbitrary P and Q. Make sense? So this is how the merge function works. Merge logic works. Now let's look at the pseudocode. So what is the pseudocode? Here is our merge algorithm. We had the B array from 0 to P minus 1. We have the C array from 0 to Q minus 1. And both these arrays are sorted. These are our input arrays. And we want to combine all these elements of B and C and put it in a sorted order in A. So the size of array will be P plus Q, and the indexing will be like 0 to P plus Q minus 1. Okay. And we take 3 pointers, I for B array, J for C array, K for A array. And they all point to 0 initially, right? 0 of B, that means the first element, 0 of B, 0 of C, and k points to 0 of A. Then we have a while loop. While I is less than P and J is less than Q. What is the meaning of this? While one of the arrays is completely scanned, right? While one of the smallest array among B and C is completely scanned, keep checking if B of I is less than or equal to C of J, right? The ith element of B is less than or equal to the jth element of C. If B of I is, say, smaller, then add the bth element to A, right? Increment the I pointer. On the other hand, the reverse case, opposite case, if C of J is less than B of I, then add the jth element of C to array A and increment the J pointer. In either case, you are adding one element to A array, right? You have to increment the K pointer, right? See, K pointer will be incremented in this case or this case. It doesn't matter because you always add one element to A. So K pointer must be incremented in any of these cases. Hence, we keep it outside. Instead of repeating the same thing in the two cases, we keep it outside. Okay, once the program control comes out of this while loop, two things can happen. So what are the two things? One of these two things can happen. I reaches the end of B array or J reaches the end of C array. It depends on which is smaller than, right? Which other array. If I reaches the end first, end of B array, then see, you have completely scanned all the B array. Maybe C array is larger like this, right? You have, so this is the B array, this is the C array. Maybe you have completed till this. So I reached P, the end of B array. Then you have a lot of elements in C, right? Say from J to Q minus 1. What you can do is copy all these elements to the A array till the end. Why? Because we know that all the elements that have been copied till now are definitely not greater than all these elements, right? And all these elements will be the greatest elements of B and C. Hence, we can copy these greatest elements of B and C in one shot, right? Using another loop. So copy these C elements to A. So similarly, you can write if J is equal to Q, if J completely scans the C array before I scans the B array, then it's the opposite case. Copy all the remaining elements of B to A, and we are done. At this end, right? A array is completely filled from 0 to P plus Q minus 1, and A array is sorted, right? So we will have the final result in A array. Make sense? Okay, now let's look at the complexity. Complexity is, the work is T of n is equal to 2T of n by 2 plus theta n. 2T of n by 2 plus theta n. Why 2T of n by 2? Because there are two function calls. Why n by 2? Because the subproblem size is reduced by a factor of 2. And why do we have theta n? Simple. Divide step is constant time, no big deal. But what about the merge step? In the merge step, B is of size n by 2, C is of size n by 2, A should be of size n. So merging all these elements into n will take what time? N time, right? So the combined step of this sorting algorithm should take n time. Hence, 2t of n by 2 plus theta n, right? Plus theta n. So if you solve it, you get n log. And how do you solve it? Try solving using iteration and substitution, and try solving this recurrence using master theorem. And depth, what is the depth? As these two function calls are called in parallel, so it's just one function call, right? If you have infinite number of processes, d of n by 2 plus theta of n, that's theta n, right? Space is 2s of n by 2 plus theta of n, right? If you solve it, you get this. Okay, any questions in merge sort? Questions? Okay, so let's move to quick sort then. So I'll skip all these things, very similar. So as I said before, though heap sort and merge sort have some of the best worst case complexity for sorting algorithms, that is n log n comparisons, right? I mean, actually there is a lower bound to show that no algorithm that is based on comparisons can do better than n log n comparisons. Any sorting algorithm, right, that you come up with that does comparisons must have n log n comparisons. You cannot do better than that. And merge sort and heap sort are kind of time optimal sorting algorithms. Optimal with respect to this running time, work, right? Work optimal sorting algorithms. What about quick sort? Quick sort, the worst case time complexity is n squared. And still, it is used as a sort function in almost every programming language. Whenever you call sort of A or A dot sort, you are indirectly calling the quick sort function. How? And why? Why will anyone use quick sort when the worst case complexity is n squared? Okay, so let's understand about this quick sort. So let's see. So we have this array, and let's apply the divide and conquer. The first step is the partition step for quick sort. What is partition? We have covered partition. What is partition? You consider a pivot element, and based on this pivot element, you split the array into two groups, left and right, such that all the elements in the left group are less than the pivot element, and all the elements in the right group are greater than the pivot element. I mean, you can say less than or equal to the pivot element and greater than or equal to the pivot element. I mean, depending on your implementation details, right? But the idea is, suppose you consider 5 as your partition element, that is pivot element. That means 5 will be here, and the function, the partition function, the partition algorithm somehow partitions this array such that 5 comes to its correct location, right? And everything on the left is less than 5, and everything on the right is greater than 5. Right? That's the partition logic. And we have understood the partition logic. We have seen Lomuto partition, and we have seen Hoare partition. And we have seen how to use the first element as the pivot element, for partition, and we have seen how to use a random element as the pivot element. Let's not consider the case of random element as the pivot element. So in the homework, in the exams, I will only consider first element as the pivot element. Okay, do not consider random element as the pivot element. And why? Because see, if you consider random element as the pivot element, I mean, there can be a lot of answers, right? N possible answers, because any random element can be any of the n elements. But we want to have an objective way to measure or evaluate. Hence, we will consider the first element of the array as the pivot element, right? So that the grading will be objective. Everybody has to use the first element as the pivot element. Hence, you cannot have different answers, right? Okay, so here also we will explain it considering first element as the pivot element. So 5 is the pivot element. Here 5 is the first element, right? All elements to the left of 5 will be less than 5. After 5 will be greater than 5. Somehow the partition logic splits the array like this. Okay, then we recursively sort the left array. We get 1, 2, 3, 4 using quicksort. We recursively sort the right array using quicksort and combine them. Combining step is dead easy here. Look at this. 1, 2, 3, 4 are definitely less than 5, and 6, 7, 8 are greater than 5. So there is, I mean, no complicated logic of combining. Just copy all these elements. 1, 2, 3, 4, 5, 6, 7, 8. Done. So the combine logic is dead easy. You can just, I mean, copy them one by one, right? Combining is nothing but copying. I mean, if you are doing an in place sorting and all this, you don't need to copy also, right? So combine step is really dead simple. If it is out of place, it's just scan or something like that. There is no complicated logic here. Combine step is dead easy. Just add all these elements in order and you're done. Partition logic was complicated, and we have seen both types of partition: low-muto partition and Hoare partition. Okay. So we really understand the algorithm already. If we understand partition, right, which is the core concept of quicksort, we understand quicksort. Because combine is nothing here. Recursively calling the function is automatically covered. It's just one line, one recursive call. Calling the partition itself is the core logic, and we have covered how to do partition, right? Where did we cover this? In the selection algorithm. So look at the beauty of this. This partition algorithm is used as part of selection algorithm. This partition algorithm is used as part of quicksort algorithm. So this is the beauty of reusing, right? In object-oriented programming in software, you have to reuse existing logic. You have to reuse existing algorithms. So we are reusing that partition algorithm again and again for different problems, right? Okay, let's recall and understand what is this partition and how does it do it. Now let's consider 8 as our pivot element, and we apply the partition for this array using the partition algorithm, and 8 will be in its correct position. After that, right, 8 will be in its correct position. All the left elements will be less than 8. Right elements will be greater than 8. And look at the elements to the left. See, 4, 5, 6, 2, 2, 3. So where is 4? 4 is here. 5 was here. So the elements are jumbled up. You really have to use the partition logic to get this array, right? You cannot directly copy all the elements less than 8 here. because the way of swapping and all can be quite different, right? Depending on, which partition algorithm you're using. Okay, then call the quicksort function on this, quicksort function on the right subarray. Now take 4 as the partition element, partition this array. So you see that 4 is in its correct position. All the elements to the left of 4 is less than 4. All the elements to the right of 4 is greater than 4. So similarly, 11 is the partition element, partition the array. So here 2 is the partition element, right? Here 6 is the partition element, 9 is the partition element, 12 is the 13 is the partition element here, so on. Let's assume we have less than or equal to, right? Okay. See, and here we are done. When the array size is 1, we are really done. Combine is just copying here 2, 2, 3, 5, 6, 7, 9, 9, 10, 12, 13, 14. Again, copy 2, 2, 3, 4, 5, 6, 7, 9, 9, 10. The partition element comes here 11, 12, 13, 14, and this is the final array, and we are done. See, though quicksort is a complicated algorithm, the core logic of quicksort is really partition. And partition, we studied it as part of selection algorithm, right? So partition is the core idea of quicksort. Okay, so let's see the code here. Sort of L to H. Suppose you're given a subarray, low to high or L to H, right? Subarray. How do you sort that subarray? If it is one element, you don't care, it's already sorted. If there are 2 or more elements, that means L is less than H. If low is less than high, that means it contains 2 or more elements. Then call the partition logic on the subarray, right? I mean, you can use randomize or whatever, but in the homework and in exams, everywhere, or even in the slides, we will use partition using first element as the pivot element, right? But in later on in implementations and all, it's good to use randomize because that gives you better performance. Okay. So when you call the partition function, it gives you an index. What is this index? So that index means that if you're applying the partition function on this, that means after calling the partition logic, A of L, right? That's the first element, right? Pivot element. Okay, let's consider pivot is equal to A of L. So that pivot element will be placed in its correct location, and all the elements here will be less than or equal to pivot. So A of L to right here, and all the elements to the right of this pivot will be greater than pivot. This is H. And the location of this, the index of this will be S. Pivot is the element, but S is the index, right? This is the location or position, but the element will be pivot. So we are interested in the location S. So this is A of L to A of S minus 1 elements. So this is the A of S element, and this is A of S plus 1 to A of H. So this is your left subarray. This is your right subarray. So left subarray is A of L to S minus 1, right? As shown here. The right subarray is S plus 1 to A of H. And pivot is in its correct position. right? So we don't need to worry about A of S. A of S is in its correct position. Now we recursively sort the left subarray and right subarray, and we are done. And partition, we don't need to explain it, right? Because we already covered two algorithms for partition in one of the previous sessions. See, what did we use? You could use Lomuto partition or Hoare partition, right? That we have already covered how that works. So we are done with quicksort. But let's analyze the complexity. What is the complexity? What is the complexity of partition? We said when we covered partition that the partition logic takes theta n time if n is the size of the array for partition. Why is this true? Whether you use Hoare partition or Lomuto partition, you are really scanning the array. Remember how the Lomuto partition works? You have the I pointer, you have the J pointer, and you keep scanning for the elements using the J pointer. And whenever some constraints are satisfied, you swap I with J, right? A of I with A of J, and increment the pointers. So it's just a scan, right? Let's say 1 or 2 scans, done. What about Hoare partition? So Hoare partition, you have 2 pointers, I pointer and J pointer. I pointer keeps going in the right direction. J pointer keeps scanning elements in the left direction. And whenever there is a crossover, you break. And this is 1 scan, I is 1 scan, J is at most 1 scan, right? This is n time. So n. Any of the partition logics that we have seen takes n time. Okay. What about the size of left subarray and right subarray? We said it is L to S minus 1. Can we say that it is of size n by 2? We cannot. We cannot. So depending on the data distribution, the partition can happen something like this. Suppose this is our array, say 5, and suppose you have 1, and suppose this is 10, 20, 30, 40, 50. Can you apply the partition logic here? What happens? 5 will be in its correct position after applying the partition logic. 1 is the element to the left of 5, and then you have 10, 20, 30, 40, 50. Right? See, look at this. The left subarray is of size 1. The right subarray is of size n minus 2. I mean, this is 1, this is 1, so n minus 2. Right? And you're calling the quicksort function on this remaining right subarray. So in the worst case, so the reduction in the subproblem's array size or subproblem size is by just a constant, not a constant factor. Right? So n minus 2 at this step, maybe in the next step, when you recursively call, you want to find the partition, right? Maybe that will just reduce by n minus 4. Then that will reduce by n minus 6. How many time steps will it take? In the worst case, it will take this much time, t of n minus 1, right? T of n minus 1. T of n minus 1. Okay, so I showed an example where it is t of n minus 2. but in the worst case, it can be just T of n minus 1. That means the other subproblem is of size 0. There are 0 elements here. The remaining subproblem has n minus 1 elements. And the partition element itself has 1 element. So n minus 1 elements in the worst case. This is the worst case. And as we have seen, for combining, suppose you're scanning, it's n. For partition, it is n. So theta n. But in the worst case, it is T of n minus 1. If you expand it, solve it, you see that the worst case complexity of quicksort is n squared. Depth, d of n minus 1 plus theta n, again it is n squared. Right? Okay, still we prefer this over merge sort or heap sort. Why? Because though the worst case is extremely bad, on the average case, right? I mean, if we use a randomized partition, I mean, there are proofs to show that randomized partition does approximately equal partitions, right? When we use randomized partition, it's really good. It partitions almost at a constant factor. You can say it divides it into something like this, where C is a constant, say approximately 2. Approximately, right? So where approximately n by 2, something like that. So then you can show that in most cases, using probabilistic analysis, that in most, with high probability, it is n log n, but the worst case remains the same, n squared, even if you use a randomized partition, right? So try this. When you implement it, use first element as the pivot and do extensive experiments. So try randomized element as the pivot and do extensive experiments. You will see that random element as the pivot gives you much better results, and quicksort using randomized partition will run faster than merge sort and heap sort in most cases. I mean, there can be a couple of cases where it is horrible, but in most cases, it will run much better. And hence, for this reason, practical reason, not for this, worst case, right? With high probability, average case is n log n. And with high probability means in almost all cases, right? So that requires a probabilistic analysis. We will not cover it. But due to that reason, quicksort is the fastest internal memory sorting algorithm. Okay, so we will stop here. We'll stop here and continue in the next session, and we will cover more divide and conquer algorithms.